Hello and welcome to our class video about relative extrema. Our learning goal is that you'll be able to locate the relative maxima and minima of a function based off of its first or second derivative. Now, there may be some words here that are a little confusing to you. Maxima is just plural of maximum and minima is just plural of minimum. So if you have two minimums, you would actually say two minima. And extrema is a plural of extremum, which is probably even more confusing word. So extremum is either a maximum or a minimum. Okay, let me just illustrate that so you have a better idea of what we mean here. So what do we mean when we say that, we're talking about a relative maximum or minimum? Well, a loose definition would be that it's a maximum or minimum compared to the points immediately on either side of it. Okay? That's not a very precise or robust mathematical definition, but it'll do for now. Let's consider this example function that I'm going to call f of x. Can you identify a point or points on f of x that might qualify as a relative maximum? We have one here and another one there. Okay? Both of those points are higher than any of the points immediately around them. Okay? How about a relative minimum? We have one of them right there. That point is lower than all the points on either side of it. Just in that immediate vicinity. It's not the very lowest point on the entire function. Now if I consider just the interval of the function that I'm showing you, the very lowest point is called the absolute minimum. So that would be over here. That's the very lowest point on for that function on the entire interval. Okay? Where is the absolute maximum, the very highest point? Well, that's over here. Notice that the absolute maximum and relative maximum could be in the same place. Okay? That point that's a relative maximum also happens to be the very highest point on the entire function for that interval. Okay, so let's look at how do we find these. So here's a flowchart that describes two different ways that we can locate a relative maximum or relative minimum on a function. But you might be thinking, well, hey, Mr. Henning, it was so easy back here. Like, you could clearly tell where the relative maximum and the relative minimum was. I mean, that was pretty obvious, duh. Well, okay, it was easy here because I showed you a graph of the function. What these two methods are useful for is when either, for example, we don't have a graph of the function. We may not have a calculator in order to graph the function. So this is how some people analyzed the shape of functions before they had a lot of calculators that made things easy. Or this is also helpful if maybe we know information about the first derivative, but we don't actually know anything about what the original function was. Okay? So that's what this is for. Both processes start off at the same place. The first step is to find the critical points. Depending on when you're watching this video, we may have already talked about what this word means, but a critical point is a possible location for a maximum or a minimum. And we locate the critical points by finding when the first derivative of the function we're interested in is equal to 0 or doesn't exist. Okay? And it's very important on each question that asks you about this that you must write that exactly. You must put f prime equals 0 or does not exist. Sometimes you can even get a point on a free response question simply for putting that because they know you understand where to look. Simply writing down the derivative and putting it equal to 0 could get you a point. But either way, it also helps you remember what you need to do. Okay? Then after we've located the critical points, we have two different tests that we can apply to locate the maximum or minimum. We have one that's based on the first derivative called first derivative test and one based on the second derivative called the second derivative test. Oh my gosh. Okay, so before we go into detail about all of those individual steps, let's just go ahead and dive into an example question, which we will do in both ways. Alright, so let's take a look at this example problem. As we do it, I'll be modeling our reading strategy, abbreviated as RADAR, that we would have previously discussed in class. So, and the first step would be to read the problem. Alright, so I will read the question. Let f of x be equal to x cubed minus 3x squared. State the x values at which f has a critical point, and classify each critical point as a relative maximum, relative minimum, or neither. Justify your answers. Alright, I have read the question. Next part, what is the question asking for? Well, it's asking me to state the x values where we find critical points. That's one thing. But it also then wants me to classify those critical points and tell what kind it is, maximum, minimum, or neither. And then I need to justify why I think so. Oh my gosh, this question wants me to do 3 things. That's why it's important to label each one of the things it's asking for so that you make sure you cover all your bases. Alright, so we know what the question's asking for. Let's go through and decode other important information so we know what to do. We'll take it in little chunks. So you can obviously identify that the function f of x is important. And so we want to state the x values at which f has a critical point. There's a key word. Okay. Where do we find the critical points? Oh yeah, that's where f prime is equal to 0 or doesn't exist. So let's go ahead and write that down in our workspace, because sometimes you could get points for just putting that. So have I made my point yet? Okay. And then we want to classify each critical point as a relative maximum, relative minimum, or neither, and justify our answers. Okay, we already got that. Alright, so that kind of gets me started on what to do. I need to find where f prime equals 0. So, what is the first derivative? What is f prime? Were you thinking 3x squared minus 6x? That's using the power rule. And we need to find where that is equal to 0 or doesn't exist. Let's consider the doesn't exist part. Is there any value of x that would cause that first derivative to be undefined? No, it's a basic polynomial. There's nothing that would cause me to divide by 0 or do anything else mathematically illegal, make the math police come after me. No, okay, I think we're good. So we don't have to worry about the non-existent cases here. We just need to find where the first derivative is equal to 0. Alright? So there's lots of ways we could solve this equation, but one that I will recommend as being generally useful is factoring, because that will be helpful if you go on to do the first derivative test after this. So go ahead and take just a couple of seconds and factor that. What could we factor out? We could factor out a 3x, then we'd have an quantity x minus 2 equals 0. Alright, so what are the two x values that would cause that equation to equal 0? How about 0 and 2? Okay, so x equals 0 and x equals 2 would be my critical points. Sometimes you'd also call those critical numbers. Okay, so those are the ones that I need to see, well, is there a maximum there, a minimum there, or neither one? Alright, well, let's figure that out. First, we'll look at how to classify these critical points using the first derivative test. So, because of that, I'm going to display that little part of the flowchart from up above on your notes. Okay? And the first step that it says that we should do is to make a sign chart, which that is to determine the sign of f prime on each interval surrounding the critical points. Now, just a note that don't do that kind of abbreviation on the AP test. CP is not necessarily an abbreviation generally accepted. You're going to avoid abbreviating, so just to make sure that your point that you make is clear. Okay, so we're looking at a number line, marking our critical points of 0 and 2, and looking for the sign of f prime and the behavior of f. Depending on when you're watching this video, we may have very much already done this kind of thing in class. If so, then just pause the video right now, fill out the sign chart, and then skip ahead in the video to where I'm done with it and see if you got it right. But I'm going to take time right now to explain the process in detail in case you're confused. Alright, so, and we're trying to find the sign of f prime. And so we're going to do that by looking at the two factors that we found before in f prime, and the 3x and the x minus 2, looking at the sign of both of those. I need to pick a number that falls in that interval. So like I could pick -1 for this interval to the left of 0 because -1 falls there. And I'm going to, in my head, plug it into those two factors. The only thing I really care about is the sign of it. So if I plug in -1 to the 3x term, that would be a negative number. That's all I care about is the sign. Okay, what about if I plug -1 into x minus 2? That would also be a negative number, and then negative times negative would be a positive number. And if f prime is a positive number, then that means that f is increasing. Okay. A shortcut chart that, depending again on when you watch the video, you may or may not have seen, okay, you may see in a little bit, but this shortcut chart can help you out a lot. We can see here that when f prime is positive, f is increasing. Okay, so let's go ahead and do the next interval. So we can consider a number of like 1. 1 is a good, awesome number between 0 and 2. Who would have thought? And so we need to consider the sign. So if I substitute 1 into the 3x term, what sign would it be? That would be positive. And if I plug 1 into x minus 2, what sign would that be? Oh, that would be a negative number. Positive times negative would be negative. And so hence f would be decreasing. You can see that from that part of the shortcut chart there. So how about you do the whole set on the interval after positive 2. Pause the video, or just for a few seconds, and then come right back and see if you got it right. Alrighty. Here's what I got. Both terms would be positive if you plugged in any number greater than 2. So overall f prime is positive and f is increasing. Great. This gives me a general idea of the shape of the function. And now we're ready to go to the next step and determine whether each critical point represents a maximum, minimum, or neither. Okay. Now we have some rules here that are in the flowchart, but don't bother trying to memorize them by just rote memory. Okay. If you superimpose a curve following the arrows, the direction of the function above it, you can tell whether there's a maximum or a minimum. I can tell that there's a maximum at x equals 0 and a minimum at x equals 2. Wow, it's just pretty clear and evident. Okay, so you can even show that on the little shortcut chart. Yeah, I can see that, oh yeah, if I draw that little curve, change from positive to negative would be a max. So there we go. You don't have to memorize them, just visualize it. Okay. So now we're ready to actually answer the question. So we'll just kind of write out these little sentences. F has a relative max at x equals 0 because something, and f has a relative minimum at x equals 2 because something. Okay, so given that we were using the first derivative test, then I need to justify my answer based on the first derivative. So I'll be saying because f prime something something something. Okay? You have to show the calculus reasoning behind it, so you can't ever justify just saying because the original function f did such and such and such. You got to show the calculus. Okay, so what did f prime do at x equals 0? Well, it changed from positive to negative, so that I can use that as my justification. Now when we write it, we're going to actually write it out. Again, we don't want to use the abbreviations. That was just so I could fit it in the flowchart. Don't abbreviate in your justifications on the AP test. So I'll say because f prime changes from positive to negative there. Okay? What about for the minimum? What is f prime doing? F prime is changing from negative to positive, so that's exactly what I'll say. F prime changes from negative to positive there. Okay? So when using the first derivative, we look for sign changes occurring at each of the critical points to identify the locations of the maximums and minimums. Okay? But what about, there's another way to do it, so let's take a look at that. We should reach the same conclusions using the second derivative test as the first derivative test. So on any given problem, you wouldn't need to do both. You can choose whichever one you like. In some cases, though, it's much easier to use one compared to the other, so you do want to be fluent in both of these tests. Okay? I'll pull up the second derivative test chart here, and being the second derivative test, guess what? We need to find the second derivative. Okay, so looking at f prime that we found before, what is f double prime? How about 6x minus 6? Yeah, okay. And we need to then determine the sign of f double prime at each critical point. Not on an interval like we did on the first derivative, but at the specific critical points that we identified. Okay, so in other words, I need to find what f double prime of 0 is and f double prime of 2 is, since those are my two critical points. Okay, well, that's just simple substitution. 6 times 0 minus 6 would be negative 6, which is less than 0. It's negative. Okay, and 6 times 2 minus 6 is positive 6, which is positive, greater than 0. Okay, great. Okay, so now we can conclude whether each one of those points represents a maximum or a minimum. Okay, but again, don't memorize those rules. Visualize it instead. Don't memorize, visualize. That sounds like a slogan. I don't know. Okay, so I see here from our shortcut chart that, second derivative positive means f is concave up, and you can see the little minimum that creates. Likewise, when f double prime is negative, f is concave down, and you can see the little maximum at the top there. Okay? So, that's pretty straightforward. And we can match them up with what we found about f double prime of 0 and f double prime of 2. And we're ready to justify our answer. Wow, that was kind of fast. So, then we need to still fill out, well, okay, what's my reason here? What's my justification? I'll have to use a different kind than I did for the first derivative test because I based it on something different. How do you think I would finish that first sentence there? Because what? Well, I based it on f double prime of 0 being negative. So, that means I can just simply write that. There's my conclusion. That's the shortest way to put it. There's lots of different ways you could put it. F double prime of 0 is negative. You could put, you want to make sure you still say f double prime. Don't say the second derivative because it's not clear exactly what derivative you're talking about. Then for x equals 2, that was because f double prime of 2 was positive. So, oops, there's a 0 there and it should be a 2. Hold on. Much better. Okay, so that's how you justify based on the second derivative test. One downside to the second derivative test, though, is that if f double prime also comes out to be 0, it's neither positive nor negative, then it reaches no conclusion. And you have to go back and try a different test. Yeah. There is such a thing as a third derivative test, fourth derivative test, higher order derivative test, but that's outside the scope of this class. So, yeah, if f double prime also equals 0, tough luck. All right, so at this point, we've completed the first 4 parts of radar, and now we just need to see if our answer is reasonable. We're pretty sure it's reasonable already because both first and second derivative tests showed us the same conclusion. But just for a little added emphasis, let's look at a graph of the function that we've been concerning ourselves with, all without a calculator. And we can see that it does have the shape that we envisioned for it. Okay? We notice it has a relative maximum at x equals 0, and, as we predicted, a relative minimum at x equals 2. So, seems to check out to me. Alright, I hope that first initial example made some good sense and will help you when you get stuck as you're working on it in class. Alright, talk to you guys later.